Welcome to this explainer. Today we're diving into a brilliant, almost deceptively simple engineering hack that's literally saving millions of dollars and massive amounts of energy worldwide. Think about it. What if you cooled massive, hyperscale data centers just by opening the door to the outside weather? It's kind of like taking your incredibly hot, overworked laptop and just setting it out on your porch on a freezing winter day. That's the fundamental idea here, just scaled up to industrial proportions. So we're going to intuitively break down exactly what this free cooling concept is, the strict weather conditions you need to actually pull it off, the massive advantages, the hidden risks, and how it's totally evolving. Here is our roadmap for today. We'll start with the core free cooling concept, look at 3 ways to capture it, the strict weather rules nature demands, the massive efficiency payoff, the hidden dangers, and finally, how AI is completely changing the game. Okay, let's jump right into section 1. What does free cooling actually mean for a high-tech facility?
So in a standard cooling system, the compressor is the heart of the whole operation. It physically squeezes refrigerant gas to reject heat, and honestly, it consumes a monstrous amount of electricity doing it. Free cooling is the clever engineering trick of just bypassing that compressor entirely. By using naturally cold external air or water to do the chilling, these facilities basically get their cooling energy for free, and the result? It drives a vital metric called power usage effectiveness, or PUE, down to an incredibly efficient 1.1 or 1.2. That basically means almost every single watt of power entering the building goes directly to the servers, not to the air conditioning.
Moving on to section 2. You can't exactly just prop open a window in a billion-dollar facility, right? Let's look at how engineers safely capture this.
Engineers have actually developed 3 distinct methods to pull this off. First up, direct free cooling. This is exactly what it sounds like. You filter the cold outside air and blow it right onto the server racks. Super efficient, but yeah, it brings the outside world inside. Second is indirect free cooling. This one uses a heat exchanger. The cold outside air chills a metal plate, and that plate chills the inside air, keeping the internal environment perfectly sealed and sterile. And finally, waterside free cooling. This uses massive cooling towers on the roof to chill a loop of water with the outside air, directly bypassing the compressor. Because water holds heat so much better than air, this waterside method is actually the most stable and popular choice for massive modern data centers today.
Now for section 3. Nature doesn't just hand out this free energy whenever we want it. There are very strict weather rules.
These building systems are monitoring the weather 24/7. To get full free cooling, which is the holy grail where compressors are 100% turned off, the outside air needs to be about 2 to 3 degrees Celsius colder than your target water temperature. So, if your servers need 15-degree water, it's got to be 12 degrees or colder outside. But hey, even if it isn't freezing, you can still use partial free cooling. Let's say it's a mild day. The outside air can naturally pre-cool the water from, say, 22 degrees down to 18 degrees. Nature just kind of takes the edge off, and then the compressors only have to do a tiny fraction of the work to finish the job.
But wait, it is definitely not just about temperature. Humidity is absolutely critical here. If the outside air is too dry and you bring it inside, you're going to generate static electricity. And in a room full of sensitive microchips, a static shock is literally a death sentence for the hardware. On the flip side, if it's too humid, you get condensation. Water droplets will literally form right on the motherboards, causing instant electrical shorts and corrosion. Because of this, automated dampers will instantly slam shut and cancel the free cooling if the humidity steps even slightly outside that strict 20 to 80% safe zone.
Let's hit section 4. If you manage to perfectly navigate all those strict rules, the payoff is just immense. By turning off the compressor, which, remember, is the biggest energy hog in the building, cooling energy consumption drops by an astonishing 80 to 90%. When you'll realize the cooling can easily account for half of a traditional data center's entire electricity bill, wiping out up to 90% of that specific cost translates to millions and millions of dollars saved every single year. It's just a staggering leap in efficiency.
And all those energy savings cascade into some really fantastic operational benefits. Your PUEs plummet, which directly helps facilities secure those highly coveted green environmental certifications. Plus, there's a huge mechanical upside. Because your heavy-duty chillers literally get to sleep for months at a time during the winter, you are drastically extending the lifespan of that wildly expensive equipment. Less wear and tear means way longer maintenance cycles and far fewer breakdowns.
But, as we'll see in section 5, letting raw, unpredictable nature into a highly sterile data center brings some terrifying risks. This is where the engineering gets seriously tough. First up, contamination. Imagine a nearby factory venting toxic gas or a forest fire blowing smoke your way. That can get sucked directly into the server room, causing rapid chemical corrosion. The fix, multi-layered HEPA and intense chemical filters. Second is thermal shock. If a vent opens too fast on a freezing day, that sudden blast of cold air causes intense physical stress and instant condensation on the hot IT boards. So engineers use incredibly precise logic dampers to gently mix the air 1% at a time. Finally, there's geography. If you build this type of facility in a tropical climate like Singapore, you'll literally never hit those low temperature targets. You've just wasted millions on equipment you can't even turn on. That is exactly why all the big tech companies are rushing to build their new hyperscale data centers in freezing locations like Ireland or the Nordics.
And finally, Section 6. Let's look at how the explosive growth of artificial intelligence is throwing a massive curveball into all these established rules.
Okay, this is absolutely fascinating. Traditional air-cooled servers are somewhat delicate. They need water delivered at a brisk 15 degrees Celsius, which means free cooling really only works when it is genuinely cold outside. But high-density AI servers? Totally different beast. They run so incredibly hot that they need direct-to-chip liquid cooling. The water coming out of an AI server rack can be 32 degrees Celsius. That's almost 90 degrees Fahrenheit. Think about the math for a second. If your goal is just to cool that water down from 32 degrees, you don't need freezing winter air anymore. A mild, 25 degrees Celsius summer breeze is actually cold enough to absorb that heat.
Talk about a massive paradigm shift. Because of their immense heat output, AI servers are ironically allowing data centers to do what used to be impossible, achieving year-round free cooling. Facilities can use the outside air not just in the dead of winter, but right through spring, autumn, and even on warm summer days, keeping those heavy compressors permanently offline.
Which leaves us with a pretty provocative question for today. For decades, the refrigeration compressor has been the undisputed king and the biggest energy glutton of the data center world. But as our technology evolves to run at vastly higher temperatures and liquid cooling becomes the global AI standard, are we witnessing the beginning of the end for the traditional compressor? Will the massive data centers of tomorrow just be silent radiators, quietly exchanging heat with a summer breeze? It's a thrilling prospect. Thanks for joining me on this explainer, and I hope you look at a cold breeze a little bit differently from now on.